So let me start talking a bit about the setup and the lore in which the story falls in. Great. So what's the setup? So this, first of all, this is a story about holographic correlators. We're dealing with holographic correlators in a specific holographic setting, which is the duality between AVS3 times S3 times K3 and synchrony in AVS3. Of course, this should be due to some CFT2. And I mean, we're in a supersymmetric setting, so it's actually a superconformal CFT2 with, in the literature, people call it the D1, D5 CFT, just because this is the brain configuration one uses to construct such a duality. Cool. Some important facts, due to the S3, the underlying superconformal theory will have some SU2 left times SU2 right. Our symmetry is going to be important. And what's our goal? What was our goal in these two sets of papers? So let's go. Let's look at the goal. The goal was to bootstrap all scalar, that's important, 4-point functions in a specific limit at strong coupling. And from holography, most of you are probably used with that. Strong coupling for us will mean the supergravity limit, in particular 3-level supergravity. So essentially we'll compute 3-level supergravity amplitudes in ADS3, and this should correspond to 4-point correlation functions in the CFT at strong coupling. So as I said, I want to compute all of them. So what do I mean by all? But to tell you that, you need to know the spectrum. In this theory, you have two types of half PPS multiplets. So we have two towers of KK modes. The first of them, and the ones that are simpler, are the tensors. And you also have the gravitons, their names. So they have these names because the tensor comes from 60, it comes from a KK reduction of a tensor field, and the graviton comes from a dimensional reduction of the graviton. So that's so they are labeled by an integer k, which labels like the KK number. They both have equal left and right moving conformal weights, which means they're scalars. Their conformal weights are equal to the SU2 spins, which turns out to imply that they are half PPS. So yeah, half PPS, which makes our life much easier. Their dimensions are protected, for instance. And what, like, from the 2D theory point of view, what differs them is the fact that, so in this theory, you have this SO21 global symmetry, which is related to the K3 compactification. And the tensor is in a fundamental representation of SO21, and the graviton is a scalar. And it turns out that the fact that the tensor transforming the fundamental makes its correlators much simpler. But okay, that's essentially the setup. We'll compute 4-point functions involving these operators here. And before we start bootstrapping, I need to talk a bit about kinematics, as every holographic correlator paper does. So let's talk a bit about kinematics. I'm going to be very brief here. kinematics. As I said, we're interested in computing correlation functions in the dual conformal field theory. In particular, we're interested about 4-point functions of some operator, which are labeled by index I. It's inserted in a given point in our two-dimensional manifold. Ci. I'll use complex coordinates to parameterize the two-dimensional flat space. And since these operators are in non-trivial representations of SU2, they have some like floating SU2 index in them. The way we usually deal with that is that we use some SU2 polarizations and contract these polarizations with the free indices, so that this correlator here will not only depend on their insertion points, but also on some polarizations related to their SU2 presentations. So these are the y's and y bar. Y is related to the SU2 left, y bar to the SU2 right. And those are the correlation functions that we want to compute. So we want to compute them as a function of z bar, y, and y bar. Now we'll do some standard CFT analysis. We can use conformal symmetry and R symmetry to extract some kinematic prefactor that in general depend on all the insertion points, all the R symmetry polarizations, and these prefactors takes into account the way in which this correlator should transform under conformal and R symmetry. And then we are left with some function G, which depends only on conformal and SU2 invariant. So it depends on the so-called conformal and R symmetry cross ratios, which I'll denote by this difference Z here, Z and Z bar. There are also some Y and Y alpha and alpha bar, sorry. No, sorry. No, I'm going to use Y and Y bar. Alpha and alpha bar, I'm sorry. And in a CFT 4-point function, that's where the dynamics lies, because these guys are conformal invariant. And so the bosonic symmetries of our model have nothing to say about this. So that's why I'll call this the dynamical function. But remember, we also have supersymmetries. That's a superconformal theory we're dealing with. And we also need to understand the constraints of supersymmetry on this dynamical function G. And it turns out that since we're dealing with external half PPS operators, which are super simple, then the consequences of supersymmetry are super simple. They are manifested in the so-called superconformal word identities, SCWY. And they're just a simple differential equation for our dynamical function G. This, and we need to compute this at the twisted locus. Alpha bar is 1 over Z bar. The statement of the superconformal word identity is that this should be equal to 0. There's also an analogous identity for Z and alpha. So we have two superconformal word identities. And these identities here, we can actually formally solve them. This implies that we can write the dynamical function G in the following form. This is equal to some function G0, which also depends on ZZ bar alpha and alpha bar. I'm going to omit the arguments. And this function G0 here is protected. It contains only protected data, plus some factor here 1 minus Z alpha, 1 minus Z bar. But notice that when you go to the twisted locus, this factor vanishes. So you can multiply, if you have this prefactor here, you can multiply this by any function h of Z bar of n alpha bar. And this is going to be a solution for the word identities for any h. And this is where the unprotected data lies. So this is what we're interested in computing from now on. That's important. And I'll call this the reduced correlator. Very important. Okay, so now we know the setting, we know the kinematics, we know what we want to compute. Let's bootstrap. So our bootstrap method relies on the use of Mellin space. And it turns out that Mellin space for our 2D theories, in particular our ADS 3 times S3 theory, it's a little subtler than the usual case in higher dimensions. And this is due to the fact that our dynamical function G here is not symmetric under the exchange of Z and Z bar. It turns out that for Mellin space to behave in the way we like it to behave, we need functions that are symmetric under Z and Z bar. But in our spectrum, we have, I haven't mentioned that, but we have some self-dual vectors. And due to the self-dual vector exchange, the symmetry is not present. And so we have to be a little smart to circumvent this issue. And the way we do that, I mean, it's kind of elementary, but it's still non-trivial and different. We just symmetrize and anti-symmetrize our function G. So we can just write G as some G plus, plus. So we want another symmetric function of Z and Z bar, but this should be the anti-symmetric part. So we just extract a Z minus Z bar. We also kind of conventionally extract a factor of U. I'm going to tell you what U is in a moment. Times some G minus, where remember this G minus is actually symmetric under Z and Z bar. So we have these two sets of functions here. Now I'm going to define. So to keep going, I need to define these variables U and V, which CFT people are probably very acquainted with them. They are like the standard conformal cross ratios. So U is Z times Z bar, and V is 1 minus Z, 1 minus Z bar. And since G plus and G minus are symmetric functions of Z and Z bar, you can actually write them as functions of U and V. They are functions of U and V, alpha and alpha bar. And now that they are functions of U and V, we can use standard Mellin space techniques. So instead of having one Mellin amplitude per correlator, in ADS3 we need two. That's the new thing about this series of works. So just use a inverse Mellin transform to define the Mellin amplitudes. It's just the same definition that everyone uses. We have some U to the power of S over 2 plus some number that depends on the external dimensions. Same thing for V. V has some power of T plus some number that depends on external dimensions. I'm not going to write it down because it's not relevant. Then we have our Mellin amplitude. We have two Mellin amplitudes, the plus and minus, or the even and odd amplitude, which will now depend on S, C, alpha and alpha bar. And then to take into account the double trace exchanges, the fact that these objects have poles at double trace exchanges too. We extract that. And we have some factors of gammas, which depends on also on the external dimensions in ICT. So that the Mellin amplitude per se only has poles due to the exchange of single traces. Amazing. So we have our Mellin amplitude. Now I can describe the bootstrap procedure. So how did we bootstrap? So now the problem is very precisely stated. We want to compute the Mellin amplitudes plus and minus for any given set of external scalar operators. And how do we do this? We have an algorithm to do that. First, the first step we start from position space. We perform the superblock expansion in our correlators. We choose a set of external operators, and then we perform the superblock expansion. And since to know the superblock expansion precisely, we also need the OPE coefficients between the half PPS operators. OPE coefficients. And where do we get these OPE coefficients from? They can be computed from supergravity. So that's non-trivial input that supergravity is giving us. Great. We have the superblock expansion, we have the OPE coefficients, we symmetrize, anti-symmetrize that, and we know how each of the exchange contributes to J plus and J minus. And then we can translate this data here into poles and residues of our Mellin amplitudes. So both M plus and minus. So from now, like from superblocks and OPE, we can derive the poles and residues of our Mellin amplitudes. We already know a lot. We know all the poles and residues, but there's missing information. What about the contact terms? So an amplitude has poles, exchange terms, and contact terms. How do we fix the contact terms? First of all, we know from flat space limit that they should be linear in S and T. So we can just write a general ansatz for the contact terms. And afterwards, we need to use supersymmetry. So we impose the superconformal Ward identities on G. So we use the superconformal Ward identities, and and then we use like this insight from the papers of Leonardo and Shinan that we can rewrite the superconformal Ward identities as different equations in Mellin space. Our Mellin amplitude should satisfy non-trivial difference equations. And it turns out that if you know the poles and residues of our Mellin amplitudes, plus the fact that they should satisfy these difference equations, this is enough to completely fix the contact terms. So the superconformal Ward identities fix all of M plus minus for us. And that's the algorithm. So, and it has worked for like every correlator in this theory. Yeah, so now we have a machine in which we input the types of operators we want, their KK moles, and it spits out for us a set of two Mellin amplitudes. That's already great. But we can be a little bit more ambitious than that. So. Be a little bit more ambitious. I mean, we can fix some sets, specific correlators, but what we really want is to find formulas for infinite families of correlators. So now I'll discuss a bit on how we can do this. First of all, I'll just like briefly mention the types of correlators we have in this theory. We can either have four tensor correlators. Those are the most simple. We can have mixed correlators. So 2 tensor and 2 graviton. And the hardest ones, the 4 graviton correlators. And of course, they can have any KK mode we want. And what we want is find the general formulas for general families of these guys. The 4 tensor and the mixed guy, we already had like some general formulas that comes from this hidden 6D conformal symmetry story. And what we did was to compare our results with theirs and their consistence. But we didn't have no 4 graviton. Like last year, no 4 graviton amplitude had been computed yet, but our code can do that. And to get now to general formulas. How do we get general formulas? To get general formulas, we need simplifying principles. We need to find some way to simplify these Mellin amplitudes in a way that if we compute lots of them, we can use pattern matching and find some formula. In the first paper, the idea we had was to consider the reduced correlators. So the H, remember, we have an H, which comes from the superconformal symmetry too. And we can also symmetrize and anti-symmetrize the H, define an H plus and H minus, the same story as before. And then from this H plus and H minus, we can write some, what we call some reduced Mellin amplitudes and plus and N minus. And then kind of experimentally, we noticed that they are much simpler than the full ones, the transfer from G. And we were actually able to, for the 4 graviton case, have enough correlators to fix the general formula for the pairwise identical correlation functions. The first paper, we were able to fix the general formula for sigma P, sigma P, sigma Q, sigma Q, for every P and Q. But as of 2024, we're not able to fix the general formula for all KK modes. That's when Francesco and Michele joined forces with us, and they found this extra simplifying principle we needed to get a full formula for any KK mode. And I'm going to quickly discuss the insights they had that allowed for this general formula. That's where the simplicity part of this talk comes in. And there's the simplification and the simplicity that was discovered in the second paper relies on 2 insights. The first of them, first insight involves instead of using standard Mellin space, using the so-called generalized Mellin space, or what is also called, or the ADS times S formalism. And this is, I mean, the precise implementation is not as straightforward, I guess, but the idea is really simple. So in the first paper, we only transform the R symmetry cross rate. No, sorry, the conformal cross ratio, right? U and V. So we had Mellin transform that sends U and V to S and T. In generalized Mellin space, we not only Mellin transform U and V, the ADS variables, but also the R symmetry cross ratios, alpha and alpha bar. And so that's the first thing that allows us to understand what's the simplest way to write these amplitudes down. They are most simply written in generalized Mellin space. So again, we have our reduced correlators, H plus and H minus, and one defines, I'm gonna use some weird symbol here, but what matters is the idea, some ADS times S transform, in which you do a discrete Mellin transform into the R symmetry cross ratio. So we have a sum over these S check variables, which are the Mellin variables conjugate to the R symmetry cross ratios, and integrate over S hat, which are the ADS Mellin variables that we are used with. And then this defines for us our generalized Mellin amplitudes, which in general depend on some S check ij, S hat ij, and S check ij. And I mean, in this weird symbol here, I have hidden a very big measure, which I'm not going to discuss because there's no point. And this S hat ij, S check ij, they will be our Mellin variables in this formalism, and they satisfy some on-shell relations. So we have these indices goes from 1 to 4 because we're dealing with 4-point functions. So we have a j equals, and this guy satisfy some relations. So we have a S check ij. Sum over j should be equal to ki, which is the ith kk mole of the external operators, minus some delta s. This is a number that we can more or less choose. And as you see, the fact that we can choose this number is going to be important in the second insight. And same thing for the ADS Mandelstam variables. So our again, j equals 1 to 4. Some ADS S ij. Now they're equal to minus ki, where this k is the ith, ki is the ith kk mole, plus some delta ADS. And for delta ADS, I'm going to tell you for H plus delta ADS is equal to 1, H minus is equal to 2. And essentially the choice of these numbers here, they're not that arbitrary. You need to choose them such that crossing acts nicely on our Mellin amplitudes, and they are different from H plus and H minus because you extract a Z minus Z bar from H minus. And that's it. That's the first insight. We use this Mellin space generalized Mellin space formalism. We have these on-shell recursion relations. That's on-shell relations.
Can you say a little more about the S check? So initially you have some expression in terms of the polarizations.
Yeah.
And that's like a polynomial.
Yeah.
So from a polynomial, you go to what kind of function of S check?
So you have.
So the Mellin amplitudes, what?
Yeah, you have. And you'll be polynomials and poles in S check. Very much analogous to the usual manual.
And why is there a sum instead of an integral in doing the transform?
You could have written it as an integral, but then it will be like, you can use some counter arguments and there'll be like a sum of residues, and that's how we cover the sum. So we can just do this to make it obvious. Great. Now to the second insight. Really brief about. The second insight is what I call the subamplitude decomposition. This second insight is better explained with an example, but it's just the statement that our amplitudes, our correlators H plus and H minus, are more simply stated as a sum of subamplitudes in which for each of the subamplitudes you extract some polarization factor. And when you extract some polarization factor, You need to choose some different on-shell relations for each of the sub-amplitudes in the as checks. But I mean, this is more easily explained here. With all these simplifying principles, we were able to get a general formula for all graviton amplitudes. And this works, that's it for 50 or more correlators. And so, as you can see, you have this structure. H minus is super simple. It's just like generalized magnetic transform of 1 over STU, which is super simple. Looks like a supergravity amplitude, which is very nice. This works well. And on the second side, the sub-amplitude decomposition, it comes in H plus. So as you can see, H plus is the sum of 3 amplitudes in which you extract a polarization dependence, a different power of the polarization for each of the amplitudes. And the fact that we extract different powers of the polarizations means that we need to use different on-shell relations for the S-checked variables for each of the sub-amplitudes. For this first one, we use delta S1, delta S equals 2, and delta S equals 3. So we have this nice structure, which is manifestly crossing symmetry, and it's constructed out of these fairly simple building blocks. And this formula works for every correlator we have tests, and a lot of them. We use some correlators to fix it, and afterward we test it for a bunch of others, and it works. So that's it.
So what are capital S, T, and U?
Oh, sorry. Thank you very much. So if you solve these constraints, as usual in MagSpace, when you solve the constraints for SIG, you get some Mellin Amplitudes variables, S and T. You have S and T for the ABS variables, some S tilde, D tilde for the S variables, and the uppercase guys are just the sum. So that's for this tilde. So the poles, they all come. We usually call them the bold variables, but I get to bold on the board, so I did uppercase.
S and S tilde are the same as after this check.
Yeah, really. Yeah.
S hat 1, 2, I guess. Check 1.
Yeah, exactly.
That's what.
So S hat 1, 2, but S
Yeah.
check 1, 2.
Yeah, S1 choose like P1, scale of P2, and then yes.
So in this case, you also expect some kind of visual rules.
We do expect hidden performance signature to hold, but this will involve a lengthy computation to check. And this show our results match the predictions of hidden conformance images. They're consistent. And that's it. It's now some brief outline, brief perspectives. There's a lot of things we can do. This theory also has some vector half PPS multiplets. We're trying to bootstrap them, me, Connor, and Maria. We can also do loops. Once we have these vectors, this would be an interesting project too. And also there's a question of stringy corrections and Virasoro Shapiro. So Shai has this paper for one type of these correlators. How would this work for the other multiplets? That's another interesting question. Those are essentially the things one can do. And that's it. Yeah, thank you. Questions?
Can I ask you one next quick question? So I'm just curious, you said that that structure reminds you of a supergravity amplitude. So if I think of ST and U as usual variables, those look like massive poles. I don't expect massive focus for them. So maybe I'm wrong with this, and interpreting that as usual and as variables.
Yeah, so you need to do the large S and T limit to recover flat space.
Okay.
And then
Yes,
it's when, yeah, and then it becomes one of STU.
Maybe you just this before. So what's the conceptual motivation for this ADS process formalism? So I guess it's like a conjecture, but I guess you have a lot of checks on it, but I guess what's the motivation for why?
I mean, it's not a conjecture, it's like an integral transform you do. I see your point, okay.
But aren't you assuming there's some kind of relationship between all the different game of
Yeah, yeah. I mean, we've written a general ansatz and we matched again rigorous bootstrap results, and then to fix the formula and then check it for a bunch of cases. But anyway, the motivation for using ADS times S is that, I mean, there's this story large KK mode story in which you can recover 10D amplitudes from large KK modes plus large SMT.
Listen, sorry, so I guess I'm wondering, is it related to this idea of this approximate, bigger formal symmetry? So for instance, A across the five is approximate 10 symmetry. Is it related to that? I guess in this case, it'd be a 60 symmetry, 60 across this three.
It's related, but it doesn't depend on that.
And maybe it'll help to say, so this F12, F34, I don't think you wrote the definition.
Yeah,
But
that's right.
that depends on the KK modes. It depends on KI. So the dependence on KI in this generalized Mellin amplitude is a lot more mild than it is in the Mellin amplitudes we were bootstrapping before. But yeah, the ability to write things in this way is general. The thing that really shows like a hidden symmetry is the fact that you get dependence only on the sum.
Oh, because about the hidden symmetry, I thought there's some idea that it's only supposed to be true in the supergravity limit, and it's not supposed to be true for any higher derivative corrections. So I guess, so would you say that the ADS process formalism would work for higher derivative corrections, or?
That it would.
Formalism, sorry.
Yeah, I mean, the formalism works. It's like an integral transform, which simplifies the amplitudes. What the hidden 60 symmetry tells you is that when you write the generating function that should reproduce all the KK mode correlators, it only depends on the both variables over there. So it should secretly come from a higher dimensional amplitude. That's a non-trivial fact. But the fact that you can do this integral transform and it simplifies amplitudes is general.
I think it wouldn't simplify things that much.
Yeah.
I guess the reason why I was asking that there's a paper by Ellis Suwan's group in China, in ADS process 5, where they use this ADS process formalism to conjecture the ADS Kursor Shapiro for all big modes. And so I guess I was just, I don't know if you totally that big, but that's wondering, because that would go beyond this progressive limit. Where naively I thought this 10D symmetry should hold.
Yeah, I can comment on that. Basically, the idea of using this formalism, if you want to have like a whole KK modes result, is that if you want to do it, in principle, you should get rid of the dependence on the KK modes. One way of doing is by doing this Mellin transform also in the ER-symmetry variables, and just basically solve that equations to remove the K dependence and back to these other variables. So you remove these K dependence, and then you just have like some constraints on these S or R symmetry things. And once you have these things in principle, well, it kind of depends whether you can actually do these things or not, but you might be able to find something which is generic for all KK modes. So that's kind of the idea, that if you have the KK modes appearing, then you have many things that can appear in the operation and so on. So you would like to get rid of this K dependence and then just have more variables working.
You can always use this structure to stratify the resorption amplitude. In the paper analysis, just capture the top and the stratification and class place limit and then second which is below, which are still from the effective action point of view in 10D, are still controlled by 10D Lorentz action. So, but then as you go below this strata, then you find ambiguities. Those are not fixed by these 10D structures.
So you do expect there's some kind of possibility to be where they consider.
Yeah.
Fine.
Any more questions or discussion points? Yeah, let's take Rodrigo again.